Today we are diving into the hidden world of energy that powers, well, just about every chemical reaction you can think of, from the simple fizz in your soda to the massive power in a rocket engine.
So let's start with a simple question you've probably experienced firsthand. Why does a hand warmer get hot when you snap it, but a cold pack gets instantly icy? It's not magic, right? It's pure chemistry in action, and it all comes down to how energy behaves. The science that explains all this is called thermochemistry. You can think of it as the official rulebook for how heat and energy flow during a chemical reaction, whether that energy is flowing out of the reaction or into it.
Okay, so to really get a grip on this, we've got to have a few key concepts in our toolkit. First things first, we need to be really clear about what we're actually looking at. We need to define the system.
First up, you've got what's called an open system. The easiest way to picture this is a pot of boiling water on a stove. It's obviously giving off energy as heat, right? But it's also losing matter in the form of steam. So both energy and matter are escaping out into the surroundings. All right, then we have a closed system. Imagine you're running a reaction inside a totally sealed flask. It can get hot or cold, so it's exchanging energy with your hand or the lab bench, but none of the actual chemicals are getting in or out. This is how we treat a ton of lab experiments. And then you've got the holy grail, really, an isolated system. In this perfect scenario, nothing gets in and nothing gets out. Not energy and not matter. A really good thermos is about the closest we get to this in the real world. Now let's meet the star of the show, enthalpy. We use the letter H for it, and it's basically the total heat content locked inside a system. But here's the catch. It's one of those things we can't actually measure directly. It's impossible to know the absolute total enthalpy. But what we can measure and what really matters is the change in enthalpy. And this, right here, is the absolute key. For most of the chemistry that happens in the real world, like a reaction just sitting in an open beaker, the heat you can actually feel and measure with a thermometer is equal to the change in enthalpy. That's why we're so obsessed with it. It gives us a direct, measurable number for the heat flow.
Okay, so we know heat moves, but where does it go? Turns out it's pretty simple. There are really only two directions it can flow, out of the reaction or into it.
And that brings us to these two big ideas. On one side, you have an exothermic reaction. Think of our hand warmer. It releases heat, which means its change in enthalpy, its delta H, is negative. The result, the surroundings get hotter. Now flip that for an endothermic reaction, like our cold pack. It absorbs heat from its surroundings, making its delta H positive. And because it's sucking heat in, the surroundings get colder.
Okay, hold on a second. This is where people get tripped up all the time. It seems like a paradox, doesn't it? If the chemicals are losing energy, why on earth do we feel things getting hotter? The secret is, you've got to remember where you're standing. The chemical system takes its stored up potential energy and converts it into heat, which it then releases out into the surroundings. And where's the thermometer? Where's your hand? It's in the surroundings. So the system's loss is the surroundings' gain. We feel that gain as a rise in temperature. So you can imagine, with labs all over the world running experiments under all sorts of different conditions, different temperatures, different pressures, how do chemists make sure they're comparing apples to apples? They need a universal standard. And that's where this comes in, the standard enthalpy change. See that little circle symbol up there? That's basically a stamp of approval. It says, hey, we measured this under standard, internationally agreed upon conditions. This way, a measurement in one lab is directly comparable to a measurement anywhere else in the world.
Okay, we've laid all the groundwork. Now we get to the really cool part, the chemist's ultimate shortcut. It's a remarkably powerful rule that lets us predict the energy of a reaction without ever having to run it in a lab. It's called Hess's Law.
So here's the big idea behind Hess's Law. It tells us that enthalpy is what we call a state function. Now that's a fancy term, but what it really means is that the total energy change of a reaction only cares about two things, where you start and where you end. The specific path you take to get from the beginning to the end, it just doesn't matter.
The best way to think about this is like climbing a mountain. Let's say the base of the mountain is your reactants and the summit is your products. You could take a short, super steep path straight up, or you could take a long, winding trail that's much less direct. Your journey would be completely different, right? But your total change in elevation from the bottom to the top would be exactly the same. Enthalpy is just like that.
So you might be thinking, okay, that's a neat trick, but why does it matter so much?
Well, it's because this incredible theoretical shortcut works perfectly hand in hand with real-world experiments. It gives us a complete picture of chemical energy.
Just look at how these two pillars of thermochemistry work together. On one hand, you've got calorimetry. That's the real hands-on measurement in the lab using a thermometer. On the other hand, you have Hess's Law, the on-paper calculation. The lab work gives us the raw data for simple reactions, but then Hess's Law lets us take that data and combine it to predict the energy for reactions that are way too slow, too dangerous, or even just plain impossible to measure directly.
And this predictive power, that's the whole game. It's what allows us to engineer more efficient fuels, design brand new materials with specific properties we want, and really understand the engine that drives our entire world. So it leaves us with this one huge question. With a tool this powerful in our hands, what can we build next?